Section 1, Turning Moment Diagrams and Flywheels. I'll start this discussion with something that you have seen. I'm sure all of you have seen this machine, which is in simple a two-wheel tractor. You may call it using different brand names. Now, what I'm interested at this point is this disc projecting out of the engine and spinning with the engine. Have you ever thought of why such a big disc is connected to the engine? Obviously, this two-wheel tractor is a vehicle. So, do all vehicles have such a big disc connected to the engine? Just think about it. Now, interestingly, this two-wheel tractor was first designed by a Sri Lankan engineer, Mr. A. Vijayavardhana, and produced by a British company called Landmaster. I'm sure you are familiar with this name, Landmaster. So, Sri Lankans call this two-wheel tractor as Landmaster. And then at the same time, the Japanese company called Kubota independently developed a two-wheel tractor. And that Kubota tractor became quite famous and popular in Sri Lanka. So these are some features of Kubota RK80 two-wheel tractor. Engine is a single-cylinder four-stroke direct injection diesel engine. And it produces 8 horsepower, that is equivalent to almost 6 kilowatts at the speed of 2,400 revolutions a minute. So the engine displacement or the engine capacity is about 440 cubic centimeters. Just keep those numbers and values in mind for the moment. As we discuss, you will be able to relate these parameters to the requirement of having such big solid disc as you see on this tractor. Now, getting back to the flywheel, that is our topic. In simple terms, it's a heavy rotating body that acts as a reservoir of energy. So it can store energy. So it's a rotating body. So obviously, it can store energy in the form of kinetic energy. So that is, for a rotating disk, it is half I omega squared. I is the moment of inertia about the axis of rotation, and omega is the angular velocity. Now, as you see, if I give a small push, then I give a bit of energy into the wheel, and the wheel continue to rotate. Now, there is no energy input to the wheel, so it has saved the energy that I gave, and then it continue to rotate by using that energy. So that is basically the storage of energy in the form of kinetic energy. Now, if you go back, this disk that we were talking about is a rotating body connected to the engine. So obviously, it should be able to store energy. So this can act as a reservoir of energy. When the machine can supply more energy than the requirement to drive a load, the flywheel can store that additional energy in it, and then it can release that stored energy whenever the energy supplied from the engine, for example, is not adequate to drive the load. So that is basically the role of the flywheel in a machine. So if you look back, the flywheel stores energy in the form of kinetic energy that is equals half I omega squared. So I is the amount of inertia, which is a geometric parameter. You can't change it. Once you design make the flywheel, I will be the same. So when you store energy, that means when you have more energy in the system, then omega has to be more. So when the flywheel is storing energy, omega is getting increased. At the same time, when the flywheel is supplying energy to the system, E will be reduced, and that means omega will also be reduced. So in flywheels, there will be a speed fluctuation depending upon whether the flywheel absorbs energy or releases energy. And accordingly, it will not help us to maintain constant speed. But of course, you will understand as we go on, it can help us to maintain the speed fluctuation within an acceptable limit. The flywheels are used in two distinct situations. First case is if the power produced by the source is at a variable rate, but what you want is a constant supply of power. So you produce at a variable rate, but you want a constant supply. So there is a mismatch. So the flywheel could help us to handle this mismatch. On the other hand, if you have a continuous supply of power, just like an electric motor, but what you want is not a constant, but a variable supply. Again, there's a mismatch. So the flywheel could help us to bridge that mismatch. So we can go through the physics and you will understand how it is done. Now, since we started our discussion with the two-wheel tractor with a single cylinder, 4-stroke diesel engine, let's first look at what's going through inside an engine. So if it is a 4-stroke engine, it has 4 strokes: intake stroke, compression stroke, power stroke, and the exhaust stroke. And each stroke takes 180 degrees of rotation of the crank. So completion of one cycle takes 180 degrees into 4. That means 720 degrees. That means 2 complete revolutions. Now within these 2 complete revolutions, the single cylinder engine produces energy only during one stroke, that is the power stroke, that is where the combustion taking place. So the power produced during this power stroke has to be used to turn the engine through the rest of the strokes. So obviously, the power production by the engine is not constant, not uniform. On the other hand, when you fix this engine to a vehicle, you need to smoothly run the vehicle. Accordingly, you expect a constant supply of power rather than fluctuating power. So what you need is a uniform power supply. Accordingly, this is a situation where power is generated at a variable rate, but what you need is a constant supply. If you look at the two-wheel tractor, obviously this is a rotating disc, as we discussed earlier. So definitely it has to be a flywheel connected to the engine, spinning with the engine. And of course, this helps us to bridge this mismatch where the power is generated at a variable rate, but you want power at a constant rate. So this is a single cylinder engine. Now, not all engines are of single cylinder. There are vehicles with multiple cylinders, mostly mid-size cars are of 4-cylinder engines. So let's see what's happening inside a 4-cylinder engine, for example. Now there are 4 cylinders connected to the same crankshaft. And as you can see, the cylinders are fired not at the same time, but at 4 different times. So the power stroke is evenly distributed across the engine cycle. So 4 cylinders means there are 4 power strokes, and these 4 power strokes are spread across 720-degree cycle, so that you have power stroke at each 180 degrees of rotation of the engine. So obviously, this will smooth out our torque production, but it will not make it completely smooth enough so that a flywheel is required in 4-cylinder engines also. So this is basically the flywheel. So take a look at this example, a punching press. So the workpiece is punched against the tool and make certain pattern on it. Penetrate the tool through the workpiece, you need more energy. But in the other times, the machine is in idle situation, so you need only small bit of energy to overcome the friction and dynamic effects and run the machine. So this is a situation where you have a constant supply of energy, but the machine doesn't need a constant supply. It needs only intermittent supply of energy. So the flywheel is required in this kind of applications also. So this is the flywheel. So it can store energy when you don't need that much of energy, and then it will supply energy back to the system when you need more energy, particularly during the punching operation. So in addition to these two applications, there are many applications of flywheels. You can see flywheels in many places. For example, rolling mills and forging machines, wind turbines to give a smooth power output, and to stabilize national grid, for example. Now in this hydropower plants, you have big rotating turbines, and in thermal power plants, you have gas turbines and steam turbines. So all these are huge rotating masses, and these rotating masses can absorb energy and supply energy, act as a flywheel. And when there are interruptions, for example, if a transmission line is stripped off, there can be a sudden drop of power, and that drop, the energy demand will be dropped instantaneously, and that drop can be absorbed by these rotating discs. And the flywheels are used as energy storage systems, and the flywheels are used in satellites for altitude control and stabilization. And also we can see flywheels in hybrid and electric vehicles, particularly as energy storage device to provide regenerative braking and things like that. So the flywheel is an essential element in many engineering applications. So in this discussion, we are going to look at how flywheel is storing energy, and how the flywheel is going to help us in minimizing the fluctuation of energy, and also how to find the minimum mass of the flywheel required in a certain application such that the speed fluctuations could be maintained within a desirable limit.